Piecewise functions. In here, we will learn how to graph piecewise defined functions and evaluate piecewise defined functions. First, let us define what a piecewise defined function is. Sometimes we come across a function that requires more than one formula in order to obtain the given output. An example of that is the absolute value function given by this expression here. We know that if we take the absolute value, for instance, of 3, the answer here is 3. It gives you always the positive value. Also, the absolute value of -3 is equal to 3. Now, this absolute value function, f of x equal to that absolute value of x, may be thought of x whenever x is positive or equal to 0. So if, for instance, in this example, when x is equal to 3, the absolute value of 3 is just equal to 3. So it is just x, so x is just equal to x. Now, if we take the absolute value of -3, that is when x is negative or less than 0, the absolute value is equal to the negative of that number. So the negative of -x. This is an example of a piecewise defined function. Now, because this requires two different processes or pieces to process the function, the absolute value function is a good example of a piecewise function. So generally, a piecewise function is a function in which more than one formula is used to define the output over different pieces of domain. Now, the graph that you see here is an example of a graph of a piecewise function. We want to find the formula for the piecewise function shown in the graph here. To answer this, we will have to take a look at the domain for each part of the graph of the function. So we will consider first this part of the graph and then consider this part of the graph here. Each part will have a definition for the function. Now let us find the equation that would describe that part of the function. Let us first consider this part here of the function, that line segment. Now, first, we will identify the domain of this line segment. We can do that by starting at this endpoint here of the line segment and drop a line perpendicular to the x-axis, and also consider this endpoint here of the line segment and drop a line perpendicular to the x-axis. This interval here on the x-axis will be the domain of that part of the graph. And this point here is -2, and this point here is 2. So therefore, for the first part of the graph, that is for the domain -2, x equals -2 up to x equals 2. Then the given function is said to be equal to 5 minus x. So you might wonder, how did we arrive at that equation or that expression? So we can obtain that expression by considering the endpoints of your line segment. We will consider the endpoints of our line segment and then get the equation of the line that contains the 2 points here. So to get the coordinates of the point here, for this endpoint here of the line segment, we have x equals -2, so we have -2, and then the y coordinate is this y value here, and that is 7. -2, 7. The other one will be x is equal to 2, and then the y coordinate is 3. Then you get the slope, so you can get the equation of the line. So you get the slope first. You get this change in y. So 7 minus 3 divided by the change in x. So you have negative 2 minus 2. So the numerator 7 minus 3 is equal to 4. Negative 2 minus 2 is negative 4. That gives you a slope of negative 1. So for that line segment, or that line segment is contained in a line whose slope is negative 1. Then you would just use one of the points here to plug in to the equation, to this equation, y minus y sub 1 equal to m times x minus x sub 1 to obtain the equation of the line. So you have y minus, I'll just pick 2, 3. So y minus 3 is equal to, our m is negative 1, times x minus our x sub 1 is 2. And then you simplify. So we have y minus 3 is equal to negative x. You distribute negative 1 to each side, or each term inside the parentheses. So you have negative 1 plus 2. And then to solve for y, you will add 3 on both sides of the equation. That gives you y equals to negative x plus 5. Hence, for x between negative 2 and 2, our f of x is equal to 5 minus x. Similarly, for this part here of the graph, we will get the domain that contains this line segment here. So you are just going to project this onto the x-axis, and this point here onto the x-axis as well. That gives us the interval between 2 to 4. Now notice that this point here is open. Okay, so therefore this x value here is not part of the domain of that piecewise function on that part of the graph. So therefore, for this portion here of the graph, the domain, or the values of x that would yield that line segment are x's between 2 to 4. So it is between 2 to 4. Now, the equation 3x minus 10 can also be computed using the same principle wherein we use these 2 points here and then get the equation of the line that contains that line segment. So to do that, we will first get the coordinates of the point. This point here, the coordinates is 2, negative 4. And this point here has the given coordinates 4, 2. And then solve for the slope. The slope is the change in y, 2 minus negative 4. Just subtract those two, divided by the difference in the x coordinate. So you have 4 minus 2. And simplifying this, we have 2 plus 4 divided by 2. So 2 plus 4 is equal to 6. Divided by 2 is equal to 3. So the slope is 3. And then you just use one of the points to plug into this formula here. Y minus y sub 1 is equal to m times x minus x sub 1. So for instance, I'm going to use 2, negative 4. So you have y minus negative 4. And the slope is equal to 3. So I'll replace m by 3. And then I have x minus, our x sub 1 will be, our x is 2. So because we use 2, negative 4. And then simplify. So you have y plus 4 is equal to 3x, distribute x inside this given parenthesis here. And then so you have 3x minus 6. And then we subtract 4 on this side of the equation to obtain y. So you do it also on this side here. Therefore, you have y is equal to 3x minus 10. Negative 6 minus 4 is minus 10. So that is how you obtain the given expression here. And so this graph here is defined by the piecewise defined function given by f of x equal to 5 minus x if x is between negative 2 and 2, and f of x is equal to 3x minus 10 if x is between 2 and 4. Now let's proceed to evaluating piecewise defined function. To evaluate a piecewise function for a given value, all you need to do is check each component of the function applies to that given value, then apply it. For example, the cost of entry to a fair C depends on the number of people P in a group. According to the piecewise function defined here, find the cost of admission for a group of 5 people. So to answer this, we will have to consider first where we could find this 5 here in the definition of our piecewise function. So notice that the piecewise function is defined to be 10p if p is between 0 and 5, including 5. And it is equal to 55 for p greater than 5. So here, this 5 is in this interval here. So therefore, we use this definition of C to compute for the desired value. So with that, we have C of 5 is equal to, the definition is 10p, so 10, and then replace p by 5. So C of 5 is equal to 50. Now suppose, for instance, we want to find the cost of admission for 10 people. So to answer that, we will have to determine where we could find 10 in the domain of the piecewise function. Is it going to be here or here? So notice that our function is defined to be equal to 55 when p is greater than 5 and 10 is greater than 5. That means that C of 10 is just equal to 55.